Hello, everyone. Welcome to this lecture of Mechanics of Solid 2. Today, we will officially start with our first topic of this course, which is called combined stresses. Now, in our Mechanics of Solid 1, we studied three basic types of loadings, which were axial, torsional, and flexure. So, axial load is equal to P by A, where P is the axial force applied on a body and A is the area. The torsional load tau is equal to T rho by J, where T is the applied torque on a body, rho is the distance of the circular fiber which we are considering, J is the polar moment of inertia. And the flexure loading is equal to my over I, where m is the bending moment, y is the distance of any fiber from the neutral axis, and I is the moment of inertia. In our previous course of Mechanics of Solid 1, we considered a body which is subject to different types of loading. This body was supported at certain position and it had variety of loads applied. The basic aim in our previous course of Mechanics of Solid 1 was to find out the internal behavior of structure under the application of a single type of loading. So, in other words, we were trying to find out the stresses and strains within a body when subjected to, say, axial load only, or torsion load only, or flexure load only. So essentially, we were studying a body under one type of loading at a time. In the combined stresses case, we will take combination of these forces and we will apply it on a body and try to find out the stresses. It's important to bear in mind that the stress strain in our course will be considered elastic. So, in the Mechanics of Solid 2, we won't exceed the elastic limit. As we are saying that in the combined stresses, we can have two or more of these type of loading acting simultaneously on a structure. There can be four possible combination of these loading. One is axial and flexural, axial and torsional, torsional and flexural, and axial and torsional. So imagine we have got a beam which is subject to flexural load and axial load at a time because of the flexural load, or in other words, load applied perpendicular to the neutral axis, flexural stresses developing in this structure. Due to the axial load applied simultaneously, we would have axial stresses developing within a structure. Now, in this figure, just for convenience, it has been shown separately. In reality, we have the load applied simultaneously on the structure. In other words, this load is broken down into the flexure case and the axial case. So imagine we have point A located at some distance from the neutral axis, and we are trying to find out the effect of both flexure and axial forces at this point. In other words, we are trying to find out the stress at point A. It is important to remember that the internal effects or internal behavior of a structure is related to finding the stresses and strains within the structure. At point A, located distance y from the neutral axis, we would have flexure stresses developing at A, which would be sigma f times dA. dA being the small infinitesimal area taken at point A. The force which is developed at point A is tensile because the region below the neutral axis is under tension. It goes without saying that sigma f would be equal to my or I, And the moment will be found for this condition by drawing the bending moment diagram and finding out the moment at A. This moment has been shown varying linearly along the cross section MN. Please note that A is located at a distance y on the cross section MN. The sigma F, which is the flexure stress, that is the stress at the cross section MN. That stress can be multiplied with the small area taken around point A, and that infinitesimal area times sigma F will give us the tensile force appearing at point A. Similarly, due to the axial forces, we would have axial stress developing at cross section MN. This axial stress will be again multiplied with dA, and we would find the force at point A due to this axial stress. After finding out the force contribution of flexure and the axial, we can now algebraically sum the forces up to find out the resultant force at point A. The fact that we can simply add the flexure effect and the axial effect is because we are applying the so-called principle of superposition. Principle of superposition tells us that we can linearly add the forces appearing in a particular direction provided that the system is elastic, or in other words, the elastic limit is not surpassed. Similar to point A, we can also consider a point B which is above the neutral axis. This point B would be under compressive flexure stress and tensile axial stress. So at point B, located at a distance y from the neutral axis, we would have flexure contribution opposite to the axial stress contribution, since the flexure is causing compression at point B and the axial stress, which is tensile in nature, is causing point B to be under tensile stress. Thus, we can write the total stress at any point along the cross section Mn equal to the axial stress contribution plus minus the flexure stress contribution. So in the combined stresses, we have to be very careful about the signs of the load. If the tensile stress is denoted by a positive sign and a compressive stress is denoted by a negative sign, the resultant stress at any point of the beam would be plus minus P by A plus minus my over I. The reason we have plus minus P by A with the first term is that whether our applied axial load is tension or compression. The reason we have plus minus with the flexure term my or I is that whether we are below or above the neutral axis. In other words, if we have the load P and the load due to flexure stresses in the same direction, then the algebraic sum would be positive. However, if we have the load P and the load due to flexure stresses in the opposite direction, then we would have a negative sign. Thus, the circling of these load is a reminder that the axial stress is uniform and of the same type all over the cross section. Whereas the magnitude of the flexure stress vary with the position. In the same manner, if we have axial and torsional combined load, torsional and flexural combined load, or axial, torsional, and flexural combined load, we have to apply the same concept as discussed over here. We have to make sure that whether the forces due to different type of loading is getting added or subtracted. So we will discuss now few examples to make this concept a bit more clear. In this problem, we have got a member which has got a straight portion and an oblique portion. The oblique portion is subjected to load of 50 kilonewton per meter and it is 2.5 meter long. The straight portion is 4 meter without any loading. We are asked to find out the state of stress at point C. Now, as we discussed previously, we have to first of all find out the reactions at A and B. Please note that at A we have got a hinge connection and at B we have got a roller connection whose resisting force is perpendicular to the longitudinal axis of the oblique member. Now, using equilibrium, we will get these reactions. So at B, we will get 97.59 kilonewton. At A, we would get 21.93 kilonewton acting vertically and 16.45 kilonewton acting horizontally. In order to find out the internal forces at C, we can cut the structure at C and put all the internal effect of the other side and omit the other side. So the portion of the member located at the right hand side will apply shear load V, axial load N and flexure moment M onto point C. So the equilibrium states the summation of Fx, summation of Fy and summation of moment of this free body must be equal to 0. Thus, we would get N is equal to 16.45 kilonewton, V is equal to 21.93 kilonewton, and M is equal to 32.89 kilonewton meter. So the normal stress would be determined by dividing this normal force by the area of the cross section, which is already given to us, that is 50 by 250 millimeter. So the axial stress will come out to be 1.32 megapascal, which is compression. The shear stress at this cross section will be equal to VQ by IB. However, since we are asked to find the stress at point C, which is located at the top of this member, at this position, the shear is 0. We know from our knowledge of mechanics of solid 1 that the shear at the ends are 0 and then it starts increasing. It becomes maximum at the center and then start reducing and comes again to 0 at the lower end. So shear at point C is equal to 0. The moment at point C would be equal to my over I. Y would be the maximum distance from the neutral axis to the extreme fiber. Sigma C would be equal to mc over I. I would be moment of inertia, which is bh cubed by 12. C would be the maximum distance, which is 250 millimeter by 2, thus 0.125 meter. Sigma C will come out to be 63.16 megapascal. In these type of calculations, it is important to take care of units. If we are using SI system, so we have to convert all the parameters in our SI system. Hence, load is converted is taken in Newton, area is taken in meters. And consistently in bending moment, we take everything in Newton and meters. Now, at point C, we have sigma C, which is 1.32 megapascal, and sigma C 63.16 megapascal. The 1.2 megapascal is coming from the normal force, and 63.16 megapascal is coming from the flexure stress. These two can be added because both are due to the compression load. Hence, our combined stress will come out to be 64.5 megapascal, and that would be in compression. Now, let us do this second example where we have got this circular rod which has a force of 500 pound applied in the y direction. This solid rod has a radius of 0.75 inches and the load is 500 pounds. So we are dealing with US customary units. We are asked to find out the stresses at point A, and point A is located right at the edge of this circular bar. In these type of questions, we have to first of all think what type of loading is applied. Correspondingly, we will find out our stresses and see whether the stresses are getting added, subtracted, or would have no influence at all. We can appreciate that this 500-pound load will cause axial stresses and flexure stresses at this point. So, in other words, we can transfer this 500-pound load via force couple system to this location. Thus, we can have 500 pounds load applied in equal and opposite direction at the location of this bend. So these two opposite 500-pound loads will cause a couple and axial load of 500 pounds. So 500 pounds have to be divided by this cross section in order to get the stress at this point. And that has been done over here. 500 divided by pi r square. R is the radius given to us. So we would get 283 psi. Now, the bending moment at point A would be equal to mc over I. The moment would be 500 pounds times 14 inches times C, which is 0.75 inch. C is 0.75 inch because A is located at the extreme fiber. And from the neutral axis till extreme fiber, we have got 0.75 inches. I is pi r 4 by 4. So that is the standard formula for moment of inertia of a solid circular section. We will get the bending stress equal to 21.13 ksi. Thus, at point A, we have a axial tension stress of 283 psi and a flexure stress of 21,126 psi. And at point A, these both are adding up because they are in the same direction. As our moment is counterclockwise, hence at point A, we would have tension, and opposite to point A, we would have compression. These both are added, and we get 21.4 ksi. Now, if we have the same problem, but this time the load is applied in the vertical direction. Now let us dissect this problem and see what type of stresses are developing. Since the load is applied vertically, so obviously we would have flexure stresses. So for convenience, we can have these two components highlighted as green and red. The red member is like a cantilever beam. We would have flexure stresses developing at the bent. The top cross section would be in tension and the bottom would be in compression. We would again use the force couple system to find out the forces at the bent location. So 800 pound would be transferred as it is, since previously we had 500 pound transferred at the bent in the same direction. In addition, we would have a couple causing counterclockwise moment. The vertical force on the green member will cause flexure stresses at point A, and this couple will cause torsional stresses at point A. In addition to that, we would have shear stresses also caused at point A due to this vertical load. So essentially, we have flexure stresses, torsional stresses, and shear stresses at point A. We know from our knowledge of mechanics of solid 1 that tau is equal to VQ over IT. Q is the first moment of area, which is A times Y bar. A is half pi r square, and Y bar would be equal to 4r by 3 pi. In order to find out the shear stress at point A, we have to take Q about the center of the circle. Q will come out to be 0.2813 inch cube. Now, the shear stress is equal to VQ over IT, and V is equal to 800 pounds. Q is 0.2813 inch cube. I is pi r4 by 4, and T, which is the width of the region, that is equal to 2 times the radius, or in other words, it is the diameter of the circular section. Plugging the values, we will get tau equal to 0.604 ksi. The width T is the width of the cross section at the point of interest, and the width of the cross section is equal to 2 times radius. That's why the radius is multiplied with 2 over here. The shear stress will come out to be 604 psi. At point A, the bending moment is 0 because point A is located at the center of the cross section. So sigma A is equal to 0. At point A, the torque will be equal to rho A. The third stress would be due to the torsional moment, which comes out to be 11,200 pound inch. So if we multiply 800 pound with 14, we will get 11,200 pound inch. Since we know the shear stress due to the torque is Tc by J, so 11,200 times C, which is the radius, remembering that point A is at radius r from the center, and divided by J, which is pi r4 by 2. Plugging the values, we will get 16.9 ksi. So now we have the shear stress, the bending stress, and the torsional stress. The bending stress is 0, so we don't have to worry about it. But we are left with two stresses, which is the shear stress and the torsional stress. If we take a small cube out of this point A, we will see that at point A we have a shear look facing down, and because of the counterclockwise torque, we would have a shear force facing down. Hence, these two are additive. Thus, we can add these two stresses and we will get 17.5 ksi. Please note that if we had bending stresses, still that wouldn't have contributed to our shear and torsional stress. The reason is that the bending stresses is made up of forces which is normal to the cross section, whereas the shear stresses is made up of forces which are within the plane of the cross section. So therefore, the bending stresses in reality wouldn't have contributed to the shear stresses.